Now our class. Let me share my screen. Is my screen visible?
Yes, sir.
Okay. So today class we will discuss about process synchronization. In the previous class, if you recollect, we discussed about how a process management will takes place, how process are scheduled, how process is created, how process is scheduled. The CPU scheduling algorithms we discussed, like first come first serve, shortest job first, shortest remaining first, round robin, priority scheduling, and so on and so forth. After that, we try to understand how processes are created, how processes are terminated using system calls like fork and exit. After that, we discuss that how a process will communicate with other process using inter-process communication like pipes, named pipes, unnamed pipes, and through other ways of communicating. Inter-process communication we discussed. Now let us now try to understand the process synchronization in today's class. This class, when an inter-process communication happens, we understood that suppose there are two processes. If it is using shared memory, A will access the same memory and B will also access the same memory, or else A will access a queue which is in the kernel and B will also access the queue in the kernel for message passing, and this queue will act as a communication medium between these two processes. So either you can do a shared memory or a message passing. This way we can communicate from one process to other process. Now, when a communication happens in synchronization, we need to understand few terminologies. Um, Communication between the process takes place through calls like send and receive primitives. There are different design options for implementing each primitive. For example, message passing may be either blocking or non-blocking. This blocking and non-blocking also known as synchronous and asynchronous. Blocking send, non-blocking send, and blocking receive, non-blocking receive. There are four categories. Blocking send says that the sending process is blocked until the message is received by the receiving process or by the mailbox. Non-blocking send is the sending process sends the message and resumes the operation. It doesn't matter until whether the message is received or not, it will not verify. The process will send and it will continue its operation. The blocking send will block until the message is received. It will not work until the message is received at the receiving end. This will not worry about the receiving end. It will just send, it will continue to work on its own. Blocking receive, the receiver blocks until a message is available. Non-blocking will retrieve either a valid message or a null. So these are the four categories of how the synchronization will work. For example, let us assume a simple example of synchronization using producer-consumer problem. When an item need to be produced, the producer will produce an item, and when an item need to be consumed, it will consume. The item will be consumed by itself, uh, provided the item is produced. Okay, the item when it is produced, it will be available for consumption. When it is consumed, then only the item will be produced. Suppose there are various scenarios here. If there are no items to consume, then consume will keep on waiting for the items to be available. Or if the production is full, then the production will stop until the consumption will take place. It cannot keep on producing, right? Whatever produced should be consumed. Is this clear? An example?
Yes, sir.
Okay. Now we need to talk one idea about buffering, whether the communication is direct or indirect. So the reason why I told producer consumer is same like sending and receiving. When a message need to be sent, it should be received. If the message should be received, it should be sent first. If the message is not sent, how it will receive? If the receiving queue is full, then the sender will not send the message, something like that. Okay. So whether the communication is direct or indirect, message exchanged by communicating process reside in a temporary queue. These queues are implemented in three ways. One is zero capacity, bounding capacity, and unbounded capacity. Zero capacity, the queue length, that is where the communication happens between two processes. The queue maximum length is zero, means there is no waiting. The messages will not wait. The sender will send or sender will block until the recipient receives a message. Once the message sent, it should be received. Then only the sender will start working from the next message. Until the sender recipient receives a message, the sender will be blocked because there is no waiting queue. Bounding capacity says that the queue has finite length of n, so n messages can wait. N messages can wait in a queue. After the n messages, then only the sender will stop. The sender will be stopped after filling the queue of n messages. Okay, so the queue is finite length n. After n messages can reside in it. If the queue is not full, then the new message will keep sending and added into the queue and placed in the queue, and the sender will continue its execution without waiting. It will keep producing the items that need to be sent and keep in the queue, which are to be waited. If the length capacity is finite, if the link is full, then the sender will block until the space available in the queue. Unbounded capacity says that the queue length is potentially infinite. You have a large amount of space available, so you can keep producing the number of messages that can wait. The sender will never block, so the sender will keep working on producing the items. So these are the three ways where the buffering will work. Usually we will work in the bounding capacity. So most of the times we will work with the bounding capacity, assuming that there are some queue length is there, and uh, we will not assume these are too extreme. Message length is zero and message length is infinity, which is not practical. But in some applications, if it is needed, we will use that. But bonding capacity is frequently what we are using. Now let us talk about process synchronization. The cooperating process is one that can affect or be affected by the other process executing in the system. Suppose this cooperating process can either directly share a logical address space or allowed to the shared data through some shared memory or message passing, then it will create some problem. Concurrent process, when they access the shared data, then if they are, because they are using shared memory and message passing, it will lead into some inconsistency. We need to come up with some mechanisms for orderly execution of cooperating process when the memory is shared, to maintain the consistency of the data. Okay, for example, let us assume that this is a producer consumer problem. Let us focus on this part first. Okay, let us focus this part first. This is a producer consumer problem. Okay, so in producer, when an item need to be produced, it will count the buffer size is equal, means the queue is full or not. If the counter is equal to the buffer size, then the producer will do nothing. It will not produce the next item. If they are not equal, then if there is a space, then the next item will be produced is kept in the buffer, which is in the queue. Buffer size is increased, count value is increased. Okay, this is how you produce an item. On the consumption side, when count is equal to 0, which means there are no items to consume, the queue is empty, there is no item to take. Then if queue is not equal to 0, then there are some items that need to be consumed. Then it will go to the buffer, item will consume, increment the buffer size of the consumption, decrement the counter. Okay, decrement the counter means you consumed one item. Is this clear how the producer consumer problem will, is it making sense?
Sir, can you explain it again?
Producer will produce an item, will keep in the buffer, increment the buffer size, maintain the count. Okay, when an item is produced, It will place in the buffer, increment the buffer size of input, increment the counter. If this count is equal to buffer size, then your queue is full, your buffer is full. Then you will not produce any item. Is this clear?
Yeah, okay, sir.
On the consumption side, you will consume an item from the buffer, okay, and decrement the counter because you consumed, you decrement the counter, then you take whatever the output of the buffer size, you change that value, and if count is equal to 0 means what? The queue is empty. There is no item to consume.
Yes, sir.
So this is consumer problem. This is a buffer producer problem. Is this clear?
Yes, sir.
Now let us say that now count is equal to 5. Count is 5. Okay. Now imagine that one item is produced. What will happen to count?
Sir, it will increase by 1.
So it will increment one value because one item is produced. Okay. Now here the count will become, it will check count is not equal to 0, which means 6. So one item is consumed. Now what is the value of count here?
5.
Here count will become 5, right? Because you produced one item, you consumed one item. So from 5 to it becomes 6. So initially the count value is 6. Now you consumed one item, it become 5. This is clear?
Yes, sir.
So if count is equal to 5, then after one produce, after one consumption, the output is 5, correct?
5.
Is this clear?
Yes, sir.
Okay. Now let us see that this is a C programming language that we are writing with the human understanding level. But when this code is executing in assembly programming language, this count is will be divided into 3 statements. Okay. This count plus plus will be divided into 3 statements in while executing in the machine level. In the assembly programming language. So initially the count will be assigned to a register in the CPU. Register will increment its value. Then the register value is stored into the count. This count plus plus is divided into these 3 statements. Likewise, count minus minus will execute. Count will be stored in register 2. The register value will decrement by one value. The register is stored in the count. In assembly programming language, you have to write one statement at a time. This statement will expand like this. Is this clear?
Yes, sir.
Okay. Now understand that these two processes are executing concurrently. Okay, these two process, producer and consumer process, they executing concurrently because they are executing at the same time, some time on process P1 and some time on process P2, and we will try to analyze what happens. Now suppose at T0, producer will come execute the statement register 1 is equal to count. So the count value is initially 5. So the 5 value is stored in register 1. Okay, the count value is initially 5. That's what we assume. If count value is equal to 5, we will assume that initially the count value is 5. So register 1 will get, after finishing the statement, register 1 will get the value of 5. Is that correct?
Yes, sir.
So T1 at time T1, let us say the producer again gets an opportunity to execute. So register will increment its value. So register 1 value is 5. So 5 plus 1, 6. So register 1 value will get 6. Okay. After this two statements, let us assume that consumer will come into its execution because of concurrent process. Consumer will come into its execution. Now count value is what here?
5.
5 only, right? Because after updating the register, the count value is not overwritten in the count. So the count value is still here, it's 5. So this 5 will store in register 2. Then at T3 time, let us assume that consumer will again take one more time, one more turn. So the register 2 value will become 5 minus 1, 4. Register 2 value will become 4. Okay. Now after a T4 time, the third statement will execute. So register 1 value will write in count, which will be 6. Count is equal to 6. At T5, register 2, whatever the value in register 2 will again overwrite in 4. So what is the value of count now?
4.
Is this correct?
No, sir.
This is not correct, because you do one produce, you produced one and you consumed one. You started with 5, so producer should increment to 6 and it should decrement to one value. The count value should be 5, not 4. But because of concurrent execution, count value should be 5, it should not be 4. Because of concurrent execution, the same variable, count variable, is accessed by both processes. Now count variable is shared between two processes. The variable is same. Both processes are executing and manipulating the count value. When concurrent processes are executing the and manipulating the same variable or same shared value, it may lead into problem. Okay, the end result is not correct. So the both process try to manipulate the variable count concurrently, which may not help us to get the correct answer. The actual value should be count 5, but we are ending up with count is equal to 4 because of concurrent execution. So this is a big problem in process synchronization. The reason why it happens is the process P producer and the process consumer is not synchronized. Okay, because of not synchronization, this problem is coming. So we need to do process synchronization in order to yield the correct result. Is that clear?
Yes, sir.
So that's where the process synchronization will come. But let me tell you guys one problem. A situation like this, when several process. So here what happens? The producer and the consumer will go in a race. Okay, will try to finish their job first. The process will put it in a race. Whoever finished the job first, uh, they are kept in the race, because the consumer did not waited until the produce finished all its statements. The consumer started executing, right? So a situation like this, where several process access and manipulate the same data concurrently, the outcome of the execution depends on which particular order the access takes place, which is called a race condition. Okay, this race conditions often lead us to a difficult situations. So to guard against this race condition, we need to ensure only one process at a time can be manipulated the variable count. To make a such guarantee, the process must be synchronized in some way. Is this clear?
Yes, sir.
Right. Now, let us try to understand the critical section problem. Consider a system consisting of n processes, P0, P1, and so on and so forth, Pn minus 1. Each process has a segment called a critical section. So, the critical section in which the process may be accessing or updating the data which is shared with at least one other process. The important feature is that when one process is executing in its critical section, no other process is allowed to execute in its critical section, which means no two processes are executing in the critical section at the same time. If producer will go into the critical section, consumer will not execute, it will wait. If consumer is going, then producer will wait. Only one process will enter into the critical section. Okay. Critical section says that when one process is executing in its critical section, no other process is allowed to execute in its critical section. No two processes will enter into the critical section at the same time. Okay, because when one process is accessing and updating the data that is shared with at least one other process, then only one process should work at a time. Does this make sense? What is critical section problem?
Sir, critical section is that common part for the process.
Yes.
Okay.
So it is something like this. When a process must request permission to enter into a critical section. Okay, so the entry section, you will enter in the critical section, you will exit, there will be reminder section. Okay, only one process will be executed into the critical section. When one process is executing in the critical section, then other process will try to do something, it will not work, it should not work. Is that clear?
Yes, sir.
We will try to see some example. Okay, so the critical section problem must satisfy three requirements. One is mutual exclusion. Mutual exclusion means if process PA is executing in its critical section, no other process can be executing in the critical sections. That is, each process should be executing in this critical section by itself. This is mutual exclusion. Is this clear? Mutual exclusion says that if PI is executing in its critical section, no other process can be executing in their critical sections. Progress says that if no process is executing in its critical section and some process wish to enter into their critical section, then only those processes that are not executing in their remainder section can participate in deciding which will enter in the critical section next. Okay. So the process which is not in the critical section, they want to enter into the critical section, they should be decided only the process that are not executing in the remainder sections. This is progress. Then the bounding weighting says that there exists a bound or a limit on the number of times that other process are allowed to enter in the critical sections after a process has made a request to enter its critical section before that request is granted. So these are the three properties that requirements that should satisfy as a solution to the critical section problem. This critical section problem can be implemented in many ways. The why this requirement is there, we will see one example. For example, assume that there is process P0 and P1. In process P0, P1, both process will create some child by calling the fork system call. So when child process is created, it should be assigned with process ID, PID. So it will assume that the next PID available is 2615. Now, because this process is available, when this both process is coming and requesting the process ID, this both process should not get the same ID. See the return 2615 for this both child process, this should not happen. The race condition is happening for assigning the PID again. This should not happen. Okay, the race condition is happening. Both child process will share the same ID. This should not happen. They should be mutually exclusive. Mutually exclusive means each process should be identified by its own unique ID. Okay, so the mutual exclusion property should be preserved. Is this clear?
Sir, can you explain it again?
See, the mutual exclusion says that if process P is executing in its critical section, no other process can be executing in this critical section. Progress says that this you understood the three requirements.
Yes, sir.
This is one example of race condition when assigning a PID, process ID. Process ID will be unique for each process, correct? Process ID will be unique for each process. Now
Yes, sir.
assume that you have two process P0, P1. P0 is calling a fork, so it will create one child process.
Yes, sir.
P1 also is calling fork, it will also create another child process. Now, the next available process identifier, PID, is 2615. Because the race condition happens, they both should not get the same ID. Here also the child process ID is 2615. Here also the child process is 2615. This should not happen. This should not happen.
Yes.
Mutually exclusive means each process, or although the child process, each process ID should be unique. They should not be same. They should be mutually exclusive. Okay.
Yes, sir.
Now, what should happen when process P1 calls a fork? When it is requesting a process ID, this should enter into a critical section, making the other process to wait. It will take one ID. Then whatever the next ID should be allotted to P1. Because both processes are trying to get the PID, this race condition is happening. If the same problem of assigning process ID will enter into a critical section, then only one process will execute, either this or this. Whichever the process will go into the critical section, then ID will be allotted to that, then the next available ID will be allotted to the other process. So the need of critical section can be discussed with this example. Is this clear?
Sir, when these are called, then one of them will go in critical section and other will wait. Sir, it is like that, or
Yes, yes. One will go into critical section, other will wait.
sir, can't we do this by giving them different PIDs?
Yes, we can do that, but the race condition may happen. This is what happened, right? When the statement is divided into these statements, concurrent process will execute. The race conditions will come into the picture. The value we will come up with different, not correct. The same race condition may happen for the child assigning the PID to the child process also.
Okay, sir.
Okay, so we will avoid that. We will discuss how we will avoid the critical section problem. How we will implement the critical section problem. We will discuss that. Okay. So one solution is mutex lock. Mutex lock is one of the good solution of critical section. The hardware based solutions to the critical section problems are complicated and generally inaccessible to the application programmers. But if you go for operating system designers, they can build some in higher level software tools to solve the critical section problem. That would be better. So the operating system based designed high level critical section problems to solve is one of the method is mutex. Mutex is the simplest form to solve the critical section problem. Mutex lock is a short form of mutual exclusion. Mutual MUT, exclusion EX, these three words from the mutual and first two words from the exclusion is taken and written as mutex lock. So what happens in this mutex lock is the logic is before entering into the critical section, process will acquire the lock before entering the critical section and will release the lock when it exists into the critical section. Okay. Suppose you are having a room, you are having a room and you are entering into the room, you will acquire the lock, you will go into the room, lock the door, get your job done. After your job done, you come out of the room and release the lock. Okay. Then one process, when it's in the critical section, other process will not enter because you have only one lock. Okay, something like this. When a process will enter into critical section, it will acquire the lock, it will put a lock. After entering the critical section, before entering the critical section, it will lock. After this job done, it will release the lock. So as long as there is no the critical section is logged, no other process will execute. Okay, is this clear? Only one process
Yes, sir.
will enter into the critical section. Okay, the logic behind lock is simply we will use a flag. We will use a flag based on available. Okay, so if available is true, then before acquiring the lock, we will enter into the critical section. We will make available false. Okay, available false means whenever available is true, then only you will enter into the critical section. Okay, whenever available is true, then only you will enter in the critical section. Make available false means the critical section is not available. Okay, when other process will come and try to enter into the critical section, will try to acquire the lock, will see that available is false, so it will keep waiting. When this available will true, when you release it, when you are releasing, you change this available is true. When available is true, then when process is coming and checking the value of available, it is true, then it will get the lock, enter into the critical section, make the available false. When any other process is coming, it will check the available variable. If it is not true, then it will keep waiting. When this will be available, as long as it is not released. Is this clear?
Yes, sir.
Okay. So the mutex lock is simply placed with one critical section, one lock. Only one lock is used. When other process will come and wait, want to enter into critical section, then it will not allow. Suppose the producer will enter in the critical section, the producer count will finish all the three statements. Now when the consumer will come in between, it will be not allowed because already the producer is executing, it will not finish. So in this example, producer will acquire the lock, it will execute because register count, the count plus plus, if this statement is kept in a critical section, this statement will execute, when the consumer is coming, this will not be executed because the critical section lock will be released after this statement only. So instead of executing here, this statement will execute. After T1, this statement will execute. Then the count value will become 6. Then only the consumer will execute. Okay, then only the consumer will execute. If that happens, then the count value will not change. Okay, so the producer will go and acquire the lock, finish all the statements, available will be false, available will be true only finishing after all the statements of the producer. Then the consumer, even though it will try to enter, it will not enter into, it will be not able to enter because the lock is not released. It will be released after all the statements executed by the producer. Then after that, the consumer will start executing its statements, which will help us to have a process synchronization. Is this clear?
Yes, sir.
Now, imagine you have only one critical section and only one lock. Now, in a multi-programming, there is multiple processes are want to use a critical section. What happens? You all stayed in the hostel, right? Imagine in the hostel, you have only one toilet. Only one person will go into the toilet and do his job and come out. Till that, the room will be locked. The toilet will be locked. What happens to the other people?
So they wait.
They will keep on waiting, right? They will keep on waiting. They will keep on checking whether the critical section is available or not, because you have only one room, you have only one lock, you have only one critical section, you have only one lock. The other people will wait, keep on waiting. This is the main disadvantages of mutex lock. The main disadvantage of the mutex lock is busy waiting. When a process is in critical section, any other process will try to enter into critical section, will loop continuously in the call to acquire. The continual looping is clearly a problem in multi-programming when many processes will executing in a single CPU core. Okay, so this busy waiting will waste some CPU cycles because it will check whether the critical section is available or not. It will keep on checking. Rather, this CPU cycles can be used for something productively, but it is wasting just to check that the critical section is available or not. This is one disadvantage. But the advantage is we are achieving process synchronization. The disadvantage is busy waiting. Does this make sense?
Yes, sir.
Okay, to overcome this problem, we will go to another concept called semaphore. In semaphore, also we can able to achieve the critical section using wait and signal. And semaphore is an integer variable with its two standard operations, wait and signal. We will try to see what a semaphore is with a simple example. I will show you with simple example. Okay. So just give me 1 second. Okay, by mistake I deleted one slide. Okay, I will tell you that. Okay, now suppose the semaphore, if it is, if s is equal to 0, if semaphore s is equal to 0, then no resource available. Let me write this. Let me write this. Okay, if semaphore s is equal to 0, then no resource is available. Okay, now let us write, if semaphore s is equal to 1, then one semaphore, one resource, one S resource is available. Okay, if S is equal to 2, which means what? Then two S resources are currently available, which means in semaphores there is not required to keep only one lock. You can keep multiple locks, so it's like multiple rooms, multiple toilets. Okay, you can have s is an integer variable. You can create as many as semaphores. Now what happens is, if s is greater than 0, greater than or equal to 0 or greater than 0, which means what? Resources is available, then grab it and decrement the value of s, decrement s by 1, which means you are entering into the, so yes, by calling function wait. Okay, so if signal is given, then increment one value by s, increment the value of s by 1. Does this make sense? Something? So in semaphores, assume that if semaphore is 0, then the resources is no resources available. If s is equal to 1, then one s resource is available. S is equal to 2, then two resources are available. If s is greater than 0, then enter into the critical section, decrement the value of s by calling wait. If the signal is given, then increment the value of s, saying that the semaphore is available. Is this clear?
Yes, sir.
Now let us now try to understand the semaphores. Okay, so the semaphore is simply with two functions, wait and signal. The signal will increment the value after releasing the semaphore. We can write here increment the value after releasing the semaphore, after coming out of the semaphore. Wait will enter into the semaphore and make the others wait. Okay, now in operating system there are two kinds of semaphores. One is, let me take the ink. One is counting semaphore and binary semaphore. The counting semaphore can range over an unrestricted domain. The value of binary semaphore can range between 0 and 1. Binary semaphore is just 0 and 1. Binary semaphores behave similarly to mutex clocks. Mutex clocks, you have true or false there. True, you enter into the critical section. False, you don't enter in the critical section. We use true or false in mutex clocks. Similarly, the true can be assigned to 1, false can be assigned to 0. The same can be implemented in a binary semaphore. What is happening in mutex? So the binary semaphore is can be behaves similar to mutex clocks. But in counting semaphore, you can have the semaphore values, a range of values. Here you see that you can have two semaphores, so two resources are available. One resource can be grabbed by one process, then other resource can be grabbed by another process. Like two rooms are available, you are entering into two rooms, no need to wait for other process. Then you can get the job done. Meanwhile, rooms can be available. If two toilets or three toilets, four toilets, depends on the need. You can have multiple resources. Semaphores are available. Semaphores can be available. Is this clear?
Yes, sir.
So the systems do not provide the meter clocks. Binary semaphores can be used instead of providing mutual exclusion. Mutual exclusion can be implemented using semaphores by including binary semaphores. Okay. So the definition of wait and signal is simply like this. The signal, it will increment the value, making sure that the semaphore is available. The wait will, if it is less than or equal to 0, it will decrement its value, saying that it is being used, the critical section is being used. So it's like multiple critical sections are we can make use of using semaphores. Now let us see some case studies. Let us see now some case studies. Let us assume that there are two processes with some constraints. So let us assume that process P1 with section A and section B, process P2 with section C and section D. There are two processes are available, each with two sections. Okay, now let us apply the semaphores in this case. Now let us assume that first case B should precede D, which means B should execute first before C should start. Okay, C should start only after B finished its execution. Now we can put a semaphore simply by semaphore S is equal to 0. We will put wait here, wait signal here, and we will give the signal S here. So signal S is 0. This value cannot be executed until the signal S value will become 1. Okay, signal S value is 0 here. Signal S, if it is 0, then this process will not execute. The value of, in order to enter into this critical section, this S should be 1. Okay, this 1, it will give only after signal. S value will be incremented 1, then only this process will stop waiting. It will start its execution. Okay, this, in order to enter, in order to C should be executed, we wrote wait of S here. Wait of S is 0. If it is 0, what is meant by wait when S is equal to 0? When S is equal to 0, no resource is available, so it will keep waiting. Process C will not execute, it will keep waiting. This process C, in order to execute that, this wait, it should be 1. It should be 1. this 1 will be given after the signal S. The signal will increment the S value to 1. After signal S value will become 1. Then only you will get a semaphore, then section C will execute. So section C will execute after B because you are giving signal yes after B, making wait the section C. Does this make sense?
Yes, sir.
So section C will not execute until section B finished its execution. So B will always precede C. Okay.
Yes, sir.
Now let us assume another example. P1, P2 cannot overlap. These two processes will not overlap. What will happen if they both should not overlap then? P1 can start first or P2 can start first. If P1 is starting first, then P2 is starting first, then P1 should wait. If P1 is starting first, then P2 should wait. Any process can start first. Any other process will start. They should not overlap. Means once P1 started, it should finish its execution. P2 should wait until it finished all its execution. If P2 is starting, P2 should finish all its execution, then P1 should wait. It should not interleave. After section C, P1 should not come. After section A, P2 should not come. P1, P2 cannot overlap. Okay. In this case, what we will do is we will take semaphore S is equal to 1. If S is equal to 1, we will put weight of S here and weight of S here. Whichever process start first. Suppose P1 starts, wait, what will happen here? S value will become, suppose P1 is starting, semaphore value, S value is 1. Here, because of wait, after wait, S value will become here 0. Because of 0, this P2 will not enter into critical section. This will keep waiting. If it is 0, then S cannot enter into the critical section. It will keep waiting. When this S should be 1 after finishing all its process. So I will give the signal here. Now let us assume that P2 started first. P2 started first. Now what will happen? The signal here, wait will become, S value will become 0, right? Now P1 will try to enter, it will not enter. It will not enter because S value, when P2 enters, S value will become 0. P2 will enter. Then you should give the signal after finishing all the process. Okay, you give the signal after finishing the process. Suppose P1 starts, S value will become 0. So P2 will wait. The S value after signal, here S value will become 1. After S value will become 1, then only the P2 will start. So P2 wait signal S value is 1 here. Now P2 will start. This will P2 C section will start only after finishing this, after getting the signal from S. Now on the other hand, suppose P2 will start. Here S value will become 0. P1 will not enter. P1, in order to enter, S value should become 1. This S value will become 1 only after finishing all this process. Here the signal value S value will become 1. After 1, then only the P1 will start its execution. So in this case, P1, P2 will not overlap. Is this clear?
Yes, sir.
So take one semaphore S is equal to 1, put wait and signal, then easily they will not be overlapped. Now let us assume the third case. A should execute before D and C should execute before B. So process P1, P2 will start executing. A should finish its execution before D starts, and C segment section should finish before B starts. Now what will happen? Now we will take two semaphores. S is equal to 0, T is equal to 0, we will assign with one value. We will keep signal S and signal T. What will happen? S value is 0 here, S value will become 1. Okay, and T is 0, T value also will become 1. Now we will write weight T and weight S. Now what happens? S value here, S value is here is 1 and T value here is 1. Okay, when these statements will work, this statement will execute after section A finished. After section A finished, signal S will be 1. And you are making weight S. Section D will start executing when S will become 1. Okay, section D will start when S will become 1, but S value is initially 0, right? S value is initially 0, so this will not execute until this becomes 1. This will become 1, S value will become 1 only after A finished its execution. After A finished its execution, then you are giving the signal making that S value will become 1, then only the D will start. So A precedes D. Likewise, suppose in this example, B will start only if T value is 1. But initially T value is 0. T value is 0, it will not work. When T value will become 1? After C is finished. After C is finished, then you are making a signal T, then T will become 1. After finishing C, only T value will become 1. Then only B will execute. So before starting B, C will finish its execution. Because you are giving the signal after finishing C, then only B will execute. So A precedes D, C precedes B. Is this clear?
Yes, sir.
So using semaphores, we can handle multiple processes, multiple critical sections at a time. You can carry out 3, 4, 5. So semaphores is a simple integer value, whereas mutex locks is a binary. You lock it, make other process wait. Here other processes are not waiting. So process P1 is executing, process P2 is executing. Depends on the condition and the critical section and the flow how we want to execute. We can write the signal and wait at appropriate places depends on our requirement. We can execute the codes in a synchronization, in a proper synchronization, process synchronization we can achieve using semaphores. Is this clear?
Yes, sir.
Okay. Now there are other methods also. Monitors is another method. You can explore by yourself. This one slide is repeated, right? Yeah, this slide is repeated. You can remove this. So I'll upload this slide. You go through the slides. If I haven't understood, you ask me. If you have any question in today's class, you let me know.
Sir, how can we implement these algorithms?
Right. You can implement in simple C, right? So I told you that. Let me share this slide. You see here, uh, the semaphore is a simple variable. It's an integer variable. You enter the critical section, you write the code whatever you want, you make sure that where you want to keep the critical section, you put weight of S while S less than or equal to 0, enter into the critical section, decrement the S. When you are giving the signal, you increment the value of S. Based on this S value, you are making sure that you are making sure that the critical section is available or not. You have to write this logic at the process. For example, the producer consumer problem, you have to write the producer to wait until it completes all its process. So in this example, where the count is creating some problem, because of this count is the shared variable, Then when you are manipulating the process of producer, the count process, you should put this value of producer and consumer into the critical section problem using the semaphore. You can write the same logic while calling this function. You write this logic inside that. You write this logic inside that producer and consumer. This will work.
Okay, sir.
Okay. So any other questions you want to ask? Okay, if no questions, then I'll upload the slide. Check that whether you'll be able to see the slides or not. Go through the slides. If you have any doubts, you ask me on Thursday's class. Okay, can you see this lecture 20 process synchronization PDF? Check your files. Lecture 20 process synchronization is there.
Yes, sir, it is there.
Okay, so go through the slides again. If you have any doubts, you ask me on Thursday class. Okay. So there is another way you can implement semaphores. I mean, like a critical section using monitors. If time permits, we'll discuss in the next class. Okay.